Yeah, good morning, one and all. I am Dr. Kiran Kumar Ganta, working as Assistant Professor in the Department of Physics, BV Radhakrishna Technology, Narsapur. Today I am going to talk about applied physics, and the topic name is Extrinsic Semiconductor. In the previous classes, I have discussed intrinsic semiconductors. We have derived the carrier concentration of intrinsic semiconductor, that is in terms of density of electrons in conduction band and density of holes in the valence band, and the carrier concentration of intrinsic semiconductor, Fermi level intrinsic semiconductor, electrical conductivity intrinsic semiconductor, energy gap of intrinsic semiconductor. In today's class, I am going to talk about extrinsic semiconductors. Generally, semiconductor is a material whose electrical properties lie between conductors and semiconductors. Semiconductors are classified into two types, intrinsic semiconductors and extrinsic semiconductor. Intrinsic semiconductor is a pure semiconductor which does not have any kind of impurities, which behaves like an insulator at 0 Kelvin and behaves like a conductor at higher temperature. And the extrinsic semiconductors are impure semiconductors. They are formed by the process of doping. Doping is a process of adding impurities. So by adding some impurities, extrinsic semiconductors are formed. Again, extrinsic semiconductors are classified into two types. They are N-type semiconductors and P-type semiconductors. So in today's class, we will discuss about extrinsic semiconductors, what are N-type semiconductors, what are P-type semiconductors, and we will discuss about the Fermi level in intrinsic semiconductors, Fermi level in N-type semiconductor, Fermi level in P-type semiconductor. So for this part, we don't have the derivations, just we have the qualitative treatment, which means there is no derivation for these concepts. For N-type semiconductor and P-type semiconductor, we don't have the derivations. We have just qualitative treatment, means we will discuss about the general term property, what are N-type semiconductors, what are P-type semiconductors, and just we will discuss about the Fermi level in N-type semiconductor and P-type semiconductors. So first we will discuss N-type semiconductor. An N-type semiconductor is when an intrinsic semiconductor is doped with a pentavalent impurity, the resultant material is termed as a N-type semiconductor. I repeat, when an intrinsic semiconductor like germanium or silicon are the tetravalent elements, means their valency is 4. When an intrinsic semiconductor is doped with a pentavalent impurity, just like an arsenic acid, phosphorus, arsenic, right? These are all pentavalent impurity atoms. Their valency is 5. So when an intrinsic semiconductor like germanium or silicon is doped with a pentavalent impurity atom, then the resultant semiconductor is termed as N-type semiconductor. Here what happens here, when a germanium atom is being replaced by arsenic atom, okay, so means we are doping with the pentavalent impurity atom. So means 4 germanium atoms form 4 covalent bonds. So there is an excess of electron. This excess of electron is known as a free electron. So in N-type semiconductor, electrons are the majority charge carriers and holes are the minority charge carriers. I repeat, in N-type semiconductor, electrons are the majority charge carriers because there is excess of electrons. Electrons are in excess. Okay, we are doping with pentavalent impurity. Penta means 5. So we are doping with a tetravalent element with a pentavalent impurity atom. So 4 germanium atoms form 4 covalent bonds with the neighboring arsenic atom. So there is an excess of electron. So free electrons. So excess of electrons in N-type semiconductor. Hence, in N-type semiconductor, electrons are the majority charge carriers and holes are the minority charge carriers. And N-type semiconductors are also known as electron donors. Since they are ready to donate the electrons, they have excess of electrons, so they can donate the electrons easily. Hence, N-type semiconductors are also known as electron donors. If you see the energy band diagram of N-type semiconductor, see this is the conduction band and this is the valency band. Okay, the bottom of the conduction band is denoted by EC and the top of the valency band is denoted by EV. So the energy difference between EC and EV is known as energy gap of the material. Okay, so in N-type semiconductor, electrons are in excess. So the excess electrons lie in energy level known as the donor energy level. Here ED is the energy of the donor energy level. Donor energy level. They are ready to donate the electrons. So in intrinsic semiconductor, even at low temperatures also, electron get excited from donor energy level to conduction band easily. So that happens at low temperatures. So at low temperature, in intrinsic semiconductor, to excite electron from valence band to conduction band, the energy provided must be equal to energy above the material. But in n-type semiconductor, even at low temperatures also, electron get excited from donor energy to conduction band. So conduction is possible even at low temperatures in n-type semiconductor. N-type semiconductor also known as electron donors. So here we don't have the derivation for this. Just I am giving the final expression directly. In n-type semiconductor, the Fermi level EF is equals to ED plus EC by 2. Means Fermi level exists at the middle of donor energy level and the conduction band. Let us take here. And the carrier concentration of intrinsic semiconductor N is equals to square root of 2Nd. Here Nd is the donor concentration into 2 pi me star kt by h square whole power of 3 by 4 exponential of Ed minus Ec by 2 kt. So this is the final expression of carrier concentration of n-type semiconductor. We don't have the derivation, just we have the qualitative treatment for n-type semiconductor. And the Fermi level exists at the middle of donor energy level and the conduction band. Now we will see the Fermi level n-type semiconductor, how it varies with temperature. In n-type semiconductor, first of all, this is the conduction band. Here Ec is bottom of the conduction band and this is the top of the valency band. Let us take this is Ed, energy of the donor energy level. So at T is equals to 0 Kelvin. This is at T is equals to 0 Kelvin. Fermi level exists at the middle of conduction band and donor energy level. Just as per the last expression, EF is equals to ED plus EC by 2. So Fermi level exists at the middle of donor energy level and the conduction band. But as temperature increases, the Fermi level shift towards the Fermi level in intrinsic semiconductor. So this is the variation of Fermi level in n-type semiconductor with respect to temperature. This is for the donor concentration 10 to the power of 21 atoms per meter cube. Means the Fermi level also varies with the donor concentration. If the donor impurity concentration is 10 to the power of 21 atoms per meter cube, so this is a variation. If the donor concentration increases, that is Nd is equals to 10 to the power of 23 atoms per meter cube. This is a variation. Means at higher temperature, the n-type semiconductor, the Fermi level in n-type semiconductor is same as Fermi level in intrinsic semiconductor. Why this happens? Because at low temperatures, the density of electrons in the conduction band is equal to the density of holes in the donor energy level. That happens at low temperatures. But at higher temperatures, what happens? Even from valency band also, electron gets excited from valency band to conduction band. So at extremely high temperatures, the density of electrons in conduction band almost equals to the density of holes in the valency band. So that is the reason Fermi level shift towards the Fermi level intrinsic semiconductor. So this is a variation of Fermi level in n-type semiconductor. Next we will discuss the p-type semiconductor. So what is a p-type semiconductor? When an intrinsic semiconductor is doped with a trivalent impurity, valence is 3. When an intrinsic semiconductor like germanium or silicon is doped with a trivalent impurity like aluminium, gallium, then the resultant semiconductor is termed as p-type semiconductor. So we are germanium is a tetravalent element, the valence is 4. We are doping with the gallium. Its valence is 3, trivalent impurity, trivalent. Okay, so here to form 4 covalent bonds, 4 electrons are required, 4 atoms are required. But there are only 3. Means there is a deficiency of electron. So the deficiency of electron is termed as a hole. I repeat, to form 4 covalent bonds, 4 electrons are required, but there are only 3. So there is a deficiency of electron. The deficiency of electron is now termed as a hole. So in p-type semiconductor, holes are the majority charge carriers and electrons are the minority charge carriers. I repeat, in p-type semiconductor, holes are the majority charge carriers and electrons are the minority charge carriers. So this is the energy band diagram of p-type semiconductor. In p-type semiconductor, there is a deficiency of electrons. Means that is ready to accept the electrons. Hence, p-type semiconductors are also known as electron acceptors. Electron acceptors. So the deficiency of electrons, known as holes, lie in energy level known as the acceptor energy level. Acceptor energy level. So even at low temperatures, electron gets excited from valence band to acceptor energy level. So the conduction is possible at low temperatures only. Right? Here at low temperatures, electron take the transition from valence band to acceptor energy level. And for this p-type semiconductor also, we don't have the derivation. So I am giving the final expression. Carrier concentration of p-type semiconductor, P is equals to square root of 2Na. Here Na is acceptor concentration, that is the impurity concentration of trivalent impurity atoms, into 2 pi mh star kT by h square, 3 by 4 exponential of EV minus EA by 2 kT. Here mh star is the effective mass of hole. And the Fermi level, EF is equals to EV plus EA by 2. Means Fermi level exists here. Fermi level exists in the middle of valence band acceptor energy level. I will show you the diagram. Again, this is a EC, bottom of the conduction band. This is top of the valence band. Acceptor energy level in p-type semiconductor. Fermi level in intrinsic semiconductor. So at T is equals to 0 Kelvin, Fermi level exists at the middle of acceptor energy level and the valence band, that is EF is equals to EA plus EV by 2. So the Fermi level varies with respect to temperature, and also impurity concentration. If Na acceptor concentration is 10 to the power of 21 atoms per meter cube, then this is a variation of Fermi level. Na is equals to 10 to the power of 21 atoms per meter cube. Right? At higher temperature, the Fermi level in p-type semiconductor is same as Fermi level in intrinsic semiconductor. Here also the same reason. At higher temperature, so the electrons also excite from valence band to conduction band. At low temperatures, the electrons get excited from valence band to acceptor energy level only. But at higher temperatures, the electrons gets excited from valence band to conduction band. So at higher temperatures, the density of electrons in conduction band is equals to density of holes in the valence band, which means at higher temperatures, p-type semiconductors behave like intrinsic semiconductor. So the Fermi level shift towards the Fermi level in intrinsic semiconductor. If the acceptor concentration N, A is equals to 10 to the power of 23 atoms per meter cube, then this is the variation of Fermi level with respect to temperature with the acceptor concentration Na is equals to 10 to the power of 23 atoms per meter cube. Right? So N-type semiconductors and P-type semiconductors are very useful in forming the PN junction diodes. Okay, a PN junction is formed with the help of a P-type semiconductor and N-type semiconductor. When an N-type semiconductor is added to P-type semiconductor, electrons diffuse from N-type to P-type. Simultaneously, holes diffuse from p-type to n-type, so that a region is formed which is known as p-n junction. So p-n junction diodes are formed with the help of p-type and n-type semiconductors. Since extrinsic semiconductors are very, very important, so p-n junction diodes are playing a vital role in the field of electronics and communication engineering. So extrinsic semiconductors are very, very important. So with this we have completed the extrinsic semiconductors part. In the next class we will discuss the Hall effect. Hall effect and application. With that we will complete the semiconductors part. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.